Okay, so here we go. We've been talking about stoichiometry. We've been writing balanced chemical equations. You guys have been doing calculating moles. I've even thrown some like a molecule problem in there. But the biggest thing is I'm hoping you get to see the connection between the amount of something and the mole ratio of something, and how we can use that to calculate an assortment of things. Okay, so that leads us to percent yields. No reaction is perfect. You're going to have a bunch of side stuff. You have extra products formed. And this really kind of reflects what we were talking about with like medicines and the production of some medications. You just produce such a tiny amount of product, and your reactants, I mean, some of the compounds that they're dealing with are probably astronomical in production costs. And so it's not even lucrative to even make the medicine. But I digress. So the reactants may not be converted to products, so they may just be sitting in there. So the very act that a chemical reaction occurs is pretty amazing, and it's something that we'll investigate just a little bit later in the semester. So your reality is that your percent yields can be very large, have a very large range. They can be from 0.001% product all the way up to 99.9%. And it just depends. It really just depends. All right, so the quantity of a product that is calculated to form when all of the limiting reagent reacts is called the theoretical yield. A lot of times with percent yields, you're going to have to calculate limiting reagents. They're going to give you the mass of both reactants. You have to figure out which one you produce the least amount of product with, and then you're going to have to go from there. The amount of product that is obtained is called the actual yield. So this is what we do in the lab, and this has to be provided. This isn't something that you're just going to know off the top of your head. Theoretical, we calculate. Okay, we calculate on paper. It's what we've been doing all afternoon. And then, of course, the lab is provided. To understand what is produced, we're going to calculate our percent yield. So let's get to a problem here. Let's get to something that gives us something to work with. Okay, let me clean this up a little bit. I'm so sorry. Okay. All right, now. Let me roll this up. Okay. So consider the following reaction. We've got sodium phosphate reacts with barium nitrate to make barium phosphate. And you'll notice that right here, there's that solid. So this is the precipitate. So that is the metathesis reactions that you guys worked with in lab. And of course the sodium nitrate. Now let's suppose we have a solution, and it contains 3.50 grams of sodium phosphate. So 3.50 grams of sodium phosphate. It's mixed with a solution containing 6.40 grams of barium nitrate. And they want us to calculate how many grams of barium phosphate, which is the precipitate, can be formed. Red flags. I've been given the mass of both reactants, so I'm going to have to determine who the limiting reagent is. Okay, so let's just go ahead and get started. So I'm going to start with our sodium phosphate. We have 3.50 grams of sodium phosphate. Oops. Okay, and I need the molar mass. So I'm hoping that I've calculated this somewhere. Yes. All right, so here it is. 163.656 grams and 1 mole of the sodium phosphate. Okay, so then I go here for my chemical equation. And I say that for every 2 moles of sodium phosphate, I have, 1 mole of barium phosphate. And then I need to calculate the mass of my barium phosphate. And so for every 1 mole of barium phosphate, I have 327.247 grams of this stuff. Okay, and so I end up with approximately 3.4993. Now, I'm not going to do any kind of rounding yet until the very, very end when I would report my final answer to my instructor. So I'm going to keep everything the way it is and make decisions later on. Okay, now I'm going to have to whip out the calculator because I'm going to have to calculate the mass of my barium nitrate. So I got 6.40 grams of barium nitrate. Okay. And I'm sorry about that kind of ugly. So barium's mass is 137.327. And then I have 2 nitrogens, and then I have 6 oxygens, because remember that 2 has to be distributed to everything. So I get a mass of like 261.315 grams in 1 mole. Okay, so again, the next step is I go to the balance point equation. So for every 3 moles of barium nitrate, so for every 3 moles of barium nitrate, I have 1 mole of barium phosphate. Okay, and then I calculate, of course, the mass. And I did that up here, so I'm just going to copy down what I got. So it's consistent. I'm using the same numbers. Consistency is a big deal with these problems. So let me write down who it is who it be I'm working with. Okay. So if we do our math, we got 6.40 divided by 261.315. And then I'm going to divide that number by 3 and then multiply times 327.247. And I get 2.672 grams of barium phosphate. Okay, now, which one of these is your limiting reagent? So, of course, we know that the barium nitrate is limiting how much material I can make. Okay, so this right here is theoretical. Okay, so that's my theoretical. Now, it's not mentioned up here in the problem, but they tell me that in the lab, we only made 2 grams. We only were able to collect 2 grams of this substance. So this right here is your actual. That's your actual yield. This is what we did in the lab, and it has to be done using instrumentation and stuff. What we're doing here on board, this is your theoretical. This is in theory. This is with, considering a perfect world. So let's go back to our equation for percent yield. Okay, and percent yield is your actual divided by your theoretical. So my actual was 2. And I divide that by the 2.672. And if you multiply that times 100, let me write this down here so that you can come back to this. And then the 2.672 grams, and I'm just going to write theory, and then multiply it times 100 because it is a percent yield, and I got 74.9% yield. That's really good for a chemical equation. Okay. I think there's another one that's in your notes, and it's talking about aspirin. So let me see if I can flounder around and find that one. And it may be that we just have to do that one. So let's kind of just do that one together right here. So I'm looking at the one that's on page. Excuse me, 311, and it kind of goes down and it talks about aspirin is made by reacting salicylic acid with acetic anhydride, and that's why aspirin is called acetylsalicylic acid. So say that 5 times fast. All right. They give us the masses. I'm going to go ahead and write the equation. So we got C7H6O3 plus C4H6O3, and that produces C9H8O4 plus H2 H3O2. So that looks like acetic acid as a byproduct. I'm assuming that this is aspirin, and this looks like salicylic acid, and that looks like acetic anhydride. So just don't quote me on that. All right, don't hold that against me if I got it wrong. But the problem says 1.5 grams of, I'm calling that salicylic acid, and 2.0 grams of acetic anhydride. Okay, and it goes on to tell me that the actual yield from the experiment was 1.5 grams. Is that what it says in the problem? Is it 1.5? I'm consulting with my assistant. Okay, yes, because I have inadvertently marked mine out like an idiot, so I don't know what I was doing. So they're telling me that you actually got 1.5 grams. Now remember, this comes from the lab, so we're going to have to calculate the theoretical. So I want you to do this. I want you to press pause, and I want you to try to perform your stoichiometry. And you know that you're going to have to do it twice because they gave you the masses of both reactants. And then when you come back, I'm going to have everything kind of worked out, and you can compare your notes with mine. Okay, so we've calculated. We took the time and performed the limiting reagent calculation. And if we start out with 1.5 grams of salicylic acid, we end up making 1.96 grams of aspirin, or acetylsalicylic acid. And then if I have 2 grams of acetic anhydride, I end up making 3.53 grams of acetylsalicylic acid, or better known as aspirin. Okay, so of course I'm going to have to choose my limiting reagent. So here this is. So that means the salicylic acid is my limiting reagent. And I'm going to use this as my theoretical. So it told me that I actually made 1.5 grams. And I theoretically produced 1.96 grams. I'm going to multiply that times 100. And I think we end up with, is it roughly a 70-ish kind of thing? Thought about 1.96. Yeah, so I end up with 76.5% yield in my aspirin. And again, that's a pretty high yield for this type of reaction. So, moral of the story, stoichiometry follows the same logic. It just depends on what you're given. I'm hoping that you saw the trends with a mass, molar mass, coefficients from the equations, the molar mass of what you're looking for. You start out with what you're given in mass. You calculate the molar mass. You use the balanced chemical equation. You go to the molar mass of your unknown, like we have done that a number of times. So it kind of repeats itself. Let the given dictate what units you use.